Before we start this tutorial, I just want you to know a little about Tensor, just enough which you could get yourself started. By end of tutorial, you are going to learn even a lot about the Tensor. Some of the resources I have placed here, so please use those resources and you can learn more about the tensors if you need it. But the key content related with tensor I have already placed in front of you, and that's honestly just enough for us to get started. So tensors are the building blocks of deep learning. You need tensor because the data which you are going to process in deep learning or any kind of machine learning is represented by tensors. It means your shopping cart data, your transactional data, your analytical data, your master data, they all can be represented as tensors. Your images, your videos, your audios, text, paragraph of text, words collections, whole documents, everything can be represented as tensor. So if we are trying to learn deep learning, the data which is going to be input and processed by the deep learning operations, that all is tensor. For that reason, we need to learn the tensor. All deep learning libraries, no matter what, if they are deep learning libraries, they are going to support tensor because tensor is the unit where the data is going to be input and layers, whatever happens in deep learning, everything is going to be operated on that data. So tensors, whenever we talk about tensors, we think about they are very close to metrics. So definitely they are metrics, but we call them a generalized metric. So tensors are kind of metrics, but they are a little different. And reason I'm bringing metrics to more in our discussion, so you can first get an idea what is metrics, because it's easy to understand metrics. So metrics are just 2D grid of numbers. You have rows and columns. As soon as you have rows and columns, that's your matrix. Size of n and m, where n are your rows and m are your columns. So a 2D grid of numbers is matrix. And depending on the n and m in your matrix, there are matrix operations available. Various matrix operations are available on your matrix data. Now we talk about the tensor. A tensor is a generalized matrix. A 0D matrix, a single number. You can have a number just 1 and you put in parentheses and you can say this is a tensor and it is the tensor. But there's a 0-degree matrix. Could be one line where you have just n is equal 1, a row, and columns you have, that is can also be represented as a 1-degree matrix. Then you have n-degree 3D matrix, more of a cube of numbers. So you can think about that you have a matrix n and m size and you have 100 of like that. So you have 100 of n times n. So 100 of n times n is basically your cube, and that can be represented as a matrix. So there could be even higher dimension. You can have even 4 of 10 of 4 of 100 of n of n. So higher dimension, it's very hard to comprehend and visualize, but tensor is a multi-dimensional array and it has to have minimum 3 dimensions in it. If you have 3 dimensions, we call it's a definitive tensor. In Python, a tensor is represented as n-dimensional array. When you say n-dimensional array, we talk about ndarray and the introduction of NumPy comes. So if you would want to take the essence of this whole all things tensor 2 statement, tensors are the input data for your deep learning, and all the data which you would want to process in your deep learning to do whatever learning you would want to perform has to be converted into data type as tensor. First. Second, tensor is a higher degree matrix. So you can think about its n-dimensional array. And these 2 things are good enough for us to jump over workbook. So for this workshop, I am using Google Colab. So for this deep learning all things tensor series, we are going to use the torch, PyTorch. So I have imported torch, and very first thing we can start looking into what is the tensor. So if you look into here, let me just stop it. So we are using torch.tensor, and we can say this value represented as the tensor. If I can say 1.0 can be represented as the tensor. I can say 1.9 is a single digit is represented as the tensor. If you will take this and you can say, what about A? And here's the problem. It means when we are talking about the tensors, it has to be numerical data. All numerical data could be integer and could be float. So one thing. Second, if you say 1, 2, 3, it is the tensor. If I will use this and I can say one more, 3, 4, 5, and I can put this thing in one bracket, now it is also a tensor. So what you are seeing here is the definition of tensor. So I will come into the cell 2 where I have this print t. So whatever the tensor we are going to define, we will print it, we will print its shape, we will print its type using the Python type, and we will also using the tensor d type. What is the data type in the tensor? So here we have defined a tensor 0, 0, 0. So it prints our tensor is a 0, 0, 0. It's a size of 3. So the shape is a size of 3. Class is a tensor which is type of PyTorch. Because if you are using deep learning, if you are using chain, or if you are using other libraries, Cafe, MXNet, you are seeing that type of tensor. So that's why it's a type of class. And finally, the data type. What kind of data is being used inside this tensor? So those things. So in whole workbook, I'm using these print methods to tell you. So it's better for you to see holistically the information. Now if I say 0.5, now you see here all the values are float, and here is still the float. And once you said 0.5, everything became uniform. If you say 0.005, as you see here, that the uniformity in the tensor has been taken care of that. Now it's a 3-element tensor, but if you will take this and you can put this whole thing in one array, now it's became 1 of 3. So you have one row of 3, otherwise it was just a 3-element tensor. So those are very simple matrix operations. So if you are here, you can actually say 1, 1, 1, 1. Now it's a 2 of 3. Now if you add one more item here, 2, 2, 2, and it's your tensor. Now if you say I want to use 2, 4, and you are going to get error, because uniformity is very important. N times M, number of rows, number of column has to have the uniform. You cannot say this kind of, if you want to add this, then you have to add something here too, means the uniformity is very important. So if you look into here, what we have, here we have a tensor of size 2, and within those tensors we have size 3 and 4. So number of rows are 3 and number of columns are 4. So looking into the tensor size gives you immediate information about the information representation. So for example, if you say I have the 1 million logs of shopping cart. So shopping cart can have 200 columns. So those 200 columns will be the 200 elements out of your 1 million rows. Here we can do little more operation about the types. So here you see that we have D type and it's a float. And what you could do is that, what if you are defining a tensor which could be a different type? And right now we have everything float, but we can say I want to define a tensor which is actually the integer. So let's define this way. Here you see that all the elements are 1, or the type here is integer. If you will decide that this integer is actually integer, and that is also the integer 32. So whether you define the D type, means your data type in the tensor is an integer 32, that's what you are going to get. So it's a 1 of 5. So you are asking the PyTorch to create a tensor of one row and 5 columns or 5 items, type integer, and automatically tensor of one row and 5 element is created for you. So this once. Now if you would want to say zeros and zeros, that all these zeros will be created. And sometimes you want to create an empty tensor, and then you want to take the new data which is being coming through various pipeline and process, and you want to say whatever data is coming, it has to be format of this given tensor. So that's the reason you are creating the ones or zero empty. Okay. Now if you say I want to create the float, you could actually create the float tensor, which we have already seen. So by default it's a float. And then so understanding zeros and one, you can actually create whatever size of tensor you. So for example, you can say I want to create a tensor of five collections of, each one is 5 rows and 5 columns, but they are the 5 collections. And here you could see that we got 1, 2, 3, 4, 5 collections of 1. If you say this number 50, then the representation is going to be very hard. And you see this dot 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 is actually compressing this information. Say, hey, this is what you could see here. 50 of 5 and 5. If you say 50 of one row, but 50 columns, and that's where you could see that 50 columns are hard to represent. So you are getting dot 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 here. So representation will be given to you in the printing time depending on whether the print of the data can be easily possible or not. After you have seen zeros and one, next comes to your rand. So it means random. So rather than filling 0 and 1, you might need some random data. So you could choose this random, and random values are added here. If you would force it, and you can say, can you actually make this new integer, and we can say integer 32. So whether you define d-type torch float or you do not, the random will automatically create the float values. And if you decide that you would want to actually type the int, you will see that int is not supported. So it means that when you are using the random values, you are going to get the float. So there are no limitations. You could actually define whatever you would want to create the random tensors depending on your need. Now we also have the rand n. So what is rand n is that you are saying that the number must be generated based on the normal distribution. So the numbers must be generated based on mean value 1 is mean value is 0 and the variance is 1, and you can learn more about the Gaussian white noise. So here I am using the rand n, but the numbers are generated based on our need and following the Gaussian white noise principle. As you see here, that whatever we are getting out here is a tensor, and if we go a little more into the tensor, we can say what is a tensor. This is our tensor. If you say, remember, this tensor is a type of 1 to 5. So you can say, can I get the tensor 0? You are going to get the first tensor, which is like a 2 or 5. So if you say what is the 0 shape, it will tell you shape of 2 and 5. So even if you are defining 10 of them, the 0 or n, whatever your number of elements will be in the first row, will be all the size of that. If you say, oh, I need to get the 0 of 0, and now you are getting, because first of the first and all these 5 numbers, and now you see this is a whole list available. Now if you say I want to get first number, and you are going to get the very first number. If you get the fifth number, which is index 4, and you could use the index 4, and that is giving you this number. If you say I want this number, basically this is the 1, 4, and you are going to get this number. So this is how you know that which actual data you would want to access, and that is needed, because if you would say I have 100 rows and each row has the 10 columns and the 10th column is the age. So if you would want to know out of 100 row means 100%, what is the age of 100%? You need to access the 100th row and the 10th index. So you need to understand that very well, why we need to know how to and where to where the actual data exists depending on your need. You can, once you have this idea, you can actually take a tensor and you convert to list. So whatever tensor we have here, as you see that we could convert it to list. So we can take a tensor, convert to list, and then whatever this object is, we can convert to a pandas data frame. And depending on our row, and here you could see that this is our data frame. But again, if you have a pandas data frame is really good for rows and columns. It's just like a n times m matrix. Here we have 1 of 2. So if we remove this, and we can say our tensor is type 2 rows and 5 columns, and if we convert this to a data frame, now we have a better way to represent our data. But if you have a tensor, you can convert that to pandas data frame. Now your DF is a pandas data frame. And now we are looking into the NumPy. Okay, in this next step, we have the NumPy ndarray, and we are going to convert that to a tensor, PyTorch tensor. Here we are creating the 3 by 3 by 3 matrix, which is ndarray. Let's create it. We are importing NumPy. Here you could see it's a 3 by 3 by 3. That's the matrix you have, and it's type of ndarray. And this nm, the ndarray matrix, is type of integer 64. Now we are converting this torch passing, and then everything became the tensor here. It is integer 64 of integer 64. NumPy ndarray, but this became a tensor. If we take this and just convert one value to 6.1, now automatically everything changed to float, because one value was the float. Now the uniformity has to apply, and all these values are represented as a decimal digit. And if we try to convert that also, everything became float, and uniformity has applied based on this representation. If you would have changed any other value, you must make sure that all that value must be the uniform. And when the tensor will be created, it will make sure whether it's a float or int. So we have already looked into the torch ones. You can use ones, you can use zeros. Now it comes the ones like. So sometimes you are creating a tensor which look like other tensor. So what first we are doing here, we are creating a tensor T, which is the size of 5 and 3. Then we are saying that let's create the new tensor, fill everything as 1, but the type is the previous tensor, like T. So what's going to happen is that it's going to create, so at this point, if we try to print T here, T1 will have this shape of T, but all the values will be filled by ones. So you see here that first one was the zeros here, size of 5, 3, and we are saying that when you create this new tensor, take the size of T, but please fill all the ones. If you say I want to have the rand, everything is a random, but your tensor is all the ones like, means everything became 1. And there could be a usage down the road where you will see that why we are using ones like. Similar to that, you also have the zeros like. So you fill the 0, but it's not a good example, but we say ones. And here, actually, you could see, we can say print T, and we can comment this line. Now it's better. So all the ones, everything filled by 0. If you say I want to have the rand, everything became 0. So ones like, zeros like. When you are creating ones, you can also define the type you would want, and then when you create the rand like, it means they use the method but convert that to rand, and then also change the type. And here, as you could see, but remember, rand like is always going to be float, so it will convert everything to be float directly. So here we had a 1, but we took the same type. So it's a 5 of 5 tensor which became all the random values. If you have a tensor, now you want to convert to NumPy, you can take the tensor to NumPy, and automatically your tensor will become the NumPy now. And here we have assigned back to t. If we wouldn't have assigned a t as a, we can say something a different assignment, then it will not convert. But here we have taken the t and we have converted it to NumPy and stored back to t. So now the t became the NumPy ndarray. So the transformation between the ndarray to tensor, torch tensor, torch to ndarray, and ndarray to torch is easily possible. So after we have covered the various types of tensor, understanding tensor's definition, now here comes the tensor operations. So as we talk about, tensors are metrics. So tensors are metrics, so all the matrix operations is going to be applied. You have a tensor first, which is size of n and m. It can only be multiplicable with other tensor of m and p. It means the column of the first tensor must be matched with the rows in the next tensor. As long as you follow that rule, it will work. And one more thing you need to understand, that a times b is not equal to b times a, n and m, because as you see that it is n times m, and if you have the m times n, then both t1 and t2 can be multiplicable, otherwise they're not, and we will check that. Here we have a tensor A of 3 of 4, and then tensor B we have 4 of 2, and we are multiplying, and here we are using the which is the matrix multiplication on the tensor. So A, B, and then result is A times B, and as you see here that random, and here result, there you go. So we have this multiplied this random matrix with this random matrix, and our result came this, and result will be 3 of 2. It means when we do a multiplication of that, the result will automatically become the n of p, and that's what you have got here, matrix multiplication. Here if you look into 3 of 4 and 4 of 2, and here you are multiplying, and if you are going to perform this operation, you will get an error, because if you see here that B A, because in this scenario the 2 is not matching with 3 here, so you are going to get this error. So if you have a matrix like this, you can actually generate the matrix multiplication same way. You can perform the matrix multiplication in the tensor similar to matrix. Next, transpose. Transpose is a way to move the tensor, and we can see that through an example. We have a 4 by 4, and if you see here that these are the rows and these are the columns, and when you transpose the matrix, rows became columns, column became rows, and that's why you take the matrix dot t and it's transpose it. Very simple operation. So after matrix multiplication, we have some arithmetic element wise operation. So when we talk about element wise, it means within the element in the matrix. Here we have A, which is ones, and then we are multiplying all the elements by 5, and that's what you are getting the result. Similar to that, you can do various, so you do multiplication, you can actually do, and here you can also use the matrix multiplication. So you have you also have the torch dot matrix multiplication. So that's actually we could validate here. When we are doing this A times B, we are getting this result, and you could actually say result equals to torch dot matrix multiplication of A comma B, and it's going to generate same thing. So whether you can use the tensor method on tensor, or you can use the torch method. They both are going to work properly. Here we are just using a exact same thing. So A and B, and we are using matrix multiplication. So your A and B is there once and random, and then multiplication is happening here. And here in this step, as you see, what we are doing is that we are creating two random 3 by 3 and 3 by 5. So the resultant matrix, this will be A times B will be 3 of 5. First we have defined this one, but we use the same A and we filled again the random value here. So if you would want to multiply A or B, or you want to multiply out because of the uniformity 3 by 3 times 3 by 3. So those can work in both ways. But if you say BA, it will not work. So if you define here B and you say A, you are going, because the 5 times 3 is not possible. So that's mistake you have to protect. Now, if you would want to store the matrix multiplication, which we have learned, and you can say, can you store this value to the out operation? And you can print out after that. So you see here that previously we are, let me do one more time hiding. So previously your out was this A, but after that your out is updated with the result value of A times B. So you could use this out, and again this is just a name. So you can say out1, and it became out1 and print the out1. So mat multiplication, say multiply two matrix and then store the result into the given matrix. And when you define a matrix, its matrix must be similar to what is required. So the out one was the 3 by 3, but once you said multiplication, the out became 3 of 5. So it's automatically, its size has been updated. That's why I really wanted to point you out very clearly. Division, quite simple. You just take the numbers and you can just divide, and then depending on your values, you can say I want to divide by 2.0, and value will become similar to that. Here we are using ones. You can choose random 2, and results going to. So division is quite simple. Similar to that, addition, you can have a you can, because these are element wise. So you are saying A, if you say A plus A, it will be a different. So A plus A versus A plus 5 times 8 times A, for example, that will work too. So now you are start combining depending on what your needs are. You can have these multiple different kinds of operations are also allowed. Subtraction, 1 and then minus point. If you say 0.1, and if you have these A and B and you want to create the whole series of matrix, you can create those. Division, either we are taking division by 0, everything became the infinite. So make sure that you understand the division by 0, but this matrix operation is automatically managed by that. There is no exception for you. If you say square root, you could generate the square root of your matrix. So if you choose the ones, then answer will always going to be 1, because square root of 1 is always going to be 1. So here the result will be 1 of 1, a square root. So let's talk about aggregation. Aggregation is the summing of all elements in the tensor. So let me note it down here, value. So that should be very clear for you. So for example, if we once, this became 4. If you choose the rand value, and the sum will be, it's a 9.9962, so it became 1.228, so it became 1.48 plus 9, so 2.3. So that's summation. So you get an idea about what is the aggregation of those items. Now we talk about the in-place operations. Variety of operations we have. So here you could say that we are using tensor, and then we are saying the add underscore, sub underscore, and you could pass directly to it. So here we are creating a tensor and we are doing the add and then add 5 to it. So all the operations are there. If you say tensor random here, and the 5 is added to it, and if we try to subtract, 5 is subtracted here. If we are going to divide 5, sorry, this is division, so 5, and then here you are using the multiplication. So you can get an idea that how these operations are applied on a given tensor. So you could use tensor, and then, so these are the very useful operations also available for the PyTorch tensor. Next comes the logical operations. The logical operations, basically these are logical operators. So we have defined here 4 by 4 tensor, it looks like that, and we are saying T is equal to the new tensor, A is not equal to 4. Let's run this first. Here we are defining all the values, as you could see here, is the ones, and we are saying that a is not equal to 4 means every element is not equals to 4, and equals to, if we say equals to 1, yes, it's true. So if we take a new tensor here and we define a is equal to torch dot tensor, sorry, and we define as a 2 rows of, and we say 1 2 3, and we say 4 5 6, and at this time we can say a equals 1. You will say 1 is true and rest of the items are false. So that's how you could say, if you would want to validate some of the data within the tensor, you can validate this. All operators are available. If you will say a is equals to and 5, you are going, 5, you will see that only 2 values, 5 and 6, are valid for this. So you can get an idea how you could apply these logical operations. Next comes the bitwise or the shift operations. Left shift, right shift. So we are defining a tensor which is 1, and then we are shifting left and right. So you see here bitwise operator. So your all 1 1 1 is becoming the 8 8 8. If you go 4 bits, it will become 16. So 1, then 2, then 4, then 8. So you are getting an idea. If you go 5, that's if now if you are changing to right side, 2, if you are using the 1, so that's, so you had 1 1 1 is a half, 0.5. If you are using 2, it's a half and half, 0.25. 3, half of that, 0.125. Then 4, again half of that, then again, so you are getting an idea that how we are 0 3 1 2. So left shift, right shift, we had here ones. If you will use the zeros here, anything you are doing, whether you are going this side, left side, or right side, your answers are 0 z. So this is a tensor which is 32 16 8. That's a tensor value, not a tensor type, tensor value. And y is your 1 1 1. So you are guiding tensor to do not shift like this way. You are guiding tensor to shift by a format. So there are 3 items. We are using the 3 items. Now we are doing the left shift here, that is z, and right shift we are, which is p. So you see here that 32 1 1 1 became double. Right side is half. Now if you would change this to, you can say, oh, I would like to use y of this. So 32 is 64, 16 double, that 2 times, and here is a 3, so 8 to the 8, and that became 64. So this is like a 1 2 3, 1 2 to the power 1, 2 to the power 2, 2 to the power 3. So that's is using similar to that. It's like a, when you use right shift, it's half, 2 to the power 1, that's where 2 to the power 2, 2 to the power 3. If we use the different tensor, which is like a float, and as you see here, we are going to see the similar results. So bitwise operator, I gave you some good variations so you could apply and you could understand it clearly. Next come the NumPy like indexing and slicing. Now we are going to learn that how we could slice the tensor. So we are defining a tensor. Here is a tensor and 4 by 4s. This is all ones are there. We want to get the first row of the tensor. So definitely you are going to get tensor 0, which will give you the first row of the tensor. If you want the first column, you will say colon, comma, and then you are getting the first column, last column, dot dot dot, negative. If you are saying the second column, if you say 0 1, you are getting the second column. And then how you could validate this thing, let's use this, and rather than using the ones, you could actually use the rand, and then that's where you will have actual values to verify. So now you see here the first row, you are getting this, so 414255 is correct. When you say first column, you are getting 0 and 44137. This value, if you decide this is the second column, I'm just writing there, and then you are going to get 5097. So that's will be 0, and it's better to write this way here, and here tensor, and you are saying that you are assigning slice plus assignment. So you are saying that this operation, which means this convert the second column to the 0 and then print tensor. So you have operated it, so the second column all became 0 here. Reshaping a tensor. Reshaping a tensor means change this tensor to look like different. So let's run this thing. So let's print shape. So if you look into here, the t dot shape is a 3 elements, 3 of 2. So it's a 3 of 2 element. Now you see that we are saying reshaping the tensor to 2 row and 3 column, and this is already 3 row and 2 column. So when you reshape it t dot view, it became the 2 rows and 3 columns. So 1, 2, 3, 4, 5, 6. This reshaping is becoming the 2 rows and 3 column. Here you are saying that print the 6 rows, and so when you say -1 means that, hey, I want these 6 rows, but whatever columns you can come up with that, I will be able to manage it. And if you decide something like that, 6 row and 1 column, what's going to happen is that the -1 will let the operation to choose how many possible columns can be created. In case of 6, you see here, because the column will be 0 because of given data. If you say 2 rows, automatic 3 columns. If you say 3 row, automatic 2 columns. Here same thing, if you say I'm making sure that the given tensor must have that many columns, rows you can adjust by yourself, and that's where you see that data is adjusted in a way that your rows and columns. However, if you choose for example, if I use here 5, and if I will use here 5, you will see that we are going to get error because the total number of elements are 3 times 2 means 6, and I'm saying convert that to 5 row and desired column, because even if I'm saying desired column, the math is not working here. So that's why this 5 will not work. Same thing if you look into here, the 10, because the total number of items are 6 and we are asking to put in 10 rows, and that is not going to work. So is reshaping operation very important, because when we deal with image data, we tend to perform the reshaping operations that you will see in later tutorials. So after the reshape, we have tensor concatenations here. So this is our t0, and we are concatenating. So here all the 1 1 1 1 2 times, and then the rest is going to be third. So here when we are trying to concatenate, the concatenation is happening, as you could see here, that the new t1, if we say print t1 dot shape, here when we concatenate it, is becoming total number of concatenation and the columns are integrated. But if you say dimension 1 means axis is change, you should make it everything as a column, and then that's how you can add your concatenation row wise or column wise by setting your dimension. After the tensor concatenation, next comes the device for the tensor. So what is device? Remember all the machine learning operations, we talk about deep learning on GPU. So these metrics are large amount of data. We need to process very large amount of mathematical operations on really these complex structures. So GPU helps us to perform these calculations in super fast, in super multi-threaded environment. It means these GPUs have tens of thousands of cores. They are hundreds of thousands of cores. So these mathematical manipulations could be very faster in a multi-threaded manner. So that's the big advantage of performing the deep learning on GPUs. So same thing when you are creating the tensor, you know where it's being created, whether it's created in a CPU memory or it's created in the GPU memory. So when we talk about the device for the tensor, we are not talking about the device as a CPU, GPU. It's actually happening in the GPU memory or the CPU memory. So as you see here, we are defining a tensor of shape 2, 3. And it's just like a variable shape. You can actually write 2, 3 here. It's same thing. So we have defined a shape of 2, 3, and we are creating a tensor of 2 by 3 t. By default, it's created on the CPU memory. It means that what if you have a GPU? It means when you are going to create the tensor on the GPU, there should be a way that you could create your tensor on the GPU. And that's what we are going to learn. And having the Colab is really going to help me, because Colab gives us free access to GPU. Very small slice, but at least we have access to GPU. Here, as you could see, that here are the resources for this Google Colab environment. I have RAM and I have disk. I do not have access to GPU. I can come here and I can say change runtime type. I can say please give me access to GPU. And again, it's free. Depending on whatever very small slice of GPU available for me to run free, I can get that GPU slice. The only issue is that whenever you are going to select the GPU, your whole runtime will be reset. So all the work we have done is actually reset. So in that scenario, we just need to only reload the PyTorch library and we will be good to go. So that's all. I have imported the torch library and we are good to go. So now we have access to GPU and we are creating a new tensor here, and this tensor is created on the CPU here. It means if we would want to create the GPU, we can actually create our tensor in the GPU too. But before we want to create a tensor on GPU, we need to know whether we have access to GPU or not. So here is the library. So you say torch.cuda is available. If the CUDA is available, CUDA is the runtime layer which sits on the hardware of your GPU. So CUDA is a runtime environment. So you install the various version of CUDA depend on applicable to your GPU hardware. So CUDA runtime gives you access to CUDA underneath runtime, and here you can say that CUDA is available. It's going to say that yeah, there is a one GPU available, and you can say what is our device name. It will say, oh, this actually GPU is the Tesla T4 and it's just same device count. So if you have device available, how many devices are there, what the device names are, and here we are getting the device name. So if you are using the CUDA, depending on your device, you just need to refer to the device as a CUDA 0. So here we are saying that device is actually the torch device and we are saying CUDA 0. If you have n GPUs, you can refer them 0, 1 to n. Depend. If you have 4 GPUs, 0, 1 to 3. So we are defining a device which is torch.device and CUDA 0. So our device is CUDA 0. And as you could see here, we can also define that the CUDA 0 is also our device. So now if we would want to create a new tensor on a GPU, we could use here. So here shape is 2 by 3. We are creating zeros, but we are saying that device must be the CUDA 0. So torch.device CUDA 0. Now you see the tensor is being created on the CPU RAM here, and very first time it takes time, but after that does not take time. After that is just very fast. So this zeros of all the 0 created and device was set to CUDA. So this device, now the tensor is created on the CUDA or the GPU. Here we have decided that device is CUDA 0 because this variable we have used. If we don't want to use the variable, we can actually use this definition where we are using CUDA as a literal and the 0 is the index of our GPU, and that will be exactly the same. And as you see here, we created once and it's on CUDA 0. So once 0, you got an idea. Here we are creating the random. Again, the device is CUDA. Random values are created. So just make sure if you are using GPU, you have to make sure that you are defining the device where this tensor has to be created. So whether you are using rand or random, all those operations to create your tensors are supported there. One example I wanted to show you. So for example, we are creating a tensor t equals to torch dot tensor. We are creating 1000 of, so we are creating a tensor of 100 times 100. Let's t, and we can say print t dot shape, and the tensor is actually created. And so here we are creating a tensor type of 1000 times 1000, and these tensors are created. Sometimes if you create a really very large tensor, for example, if you see that this, and you are creating 10,000, 100,000 of 10,000 and 10,000, and you might see that there is a spike in memory, and it is possible that we crashed because there was not enough RAM available for us to create the tensor of like that. So I wanted to show you that when you are creating the tensor, you are limited by the memory is given by your runtime environment. So that is very important, and in order to make it work, we have to add the import torch because our environment is recent. So that should be clear for you to understand that you are limited with the memory available for you to creating tensor because our system was crashed. So I am going to import the torch again, and I'm also going to define the CUDA for us back. So this is our device is defined, CUDA 0 is defined. So this CUDA 0 is basically our device. Next, we are creating this M1 and M2, and we are doing this operations, and this operation is going to happen at the GPU because these both of these matrix or the tensors are created. Matrix is not a good word because they are definitely the tensor. They are created and the addition is happening here. So for example, at this time we will try to say M1 plus M2, and then we can say the next operation is M0 equals M0 times M0. We are multiplying, and this will be very fast because very first time it took some time. So operation, we are performing everything on the GPU, must be clear. Next operation comes that moving tensor from GPU to CPU or CPU to GPU. So here you see in our scenario, we had this M0, which was the GPU. Now we are saying M0 move to CPU, and M0 is CUDA, M00 is on CPU. When you do not say the device type is what, is definitely the CPU. So what I want to show you here, that whether you are saying M0.CPU, but you are not assigning. So even in that scenario, the M0 is still on the CUDA. Once you say M0 equals M0.CPU, now you have moved the M0 from CUDA to CPU, and in that case the M0 is out from the GPU now. Previously it was still on the GPU and CPU because M0 and M00. So you have to, if you are moving completely between GPU to CPU, CPU to GPU, make sure you are doing perfect assignment. Next comes the bridge with NumPy. So let me explain this nicely. So at this point we are creating a tensor, all are ones. Then we are taking this tensor t, converting it to NumPy, and that NumPy ndarray is the n. So this n is actually connected with the t. So they both are connected, and they both are explicitly on the CPU because we are not talking about the GPU. So they both are on the CPU. So you see here, t is one original tensor, and it also the NumPy version of n1, but they all are same. Now we are adding 1 in the t tensor. So the tensor 1 will be added, and technically we are not touching the NumPy, but because they are bridged, they are connected, so your NumPy will also be updated now. So you only did add 1, and your NumPy is also has the same action because the NumPy is connected with the n. Okay, now what you do is that, because in case of n is your ndarray, so if you are performing additions, because add 1 is a TensorFlow operation. Add 1 is not the NumPy operation. So if you try to say n, and you will say add, and you will say, you will not, because the add 1 is not an operation for the NumPy array or ND array. So make sure you understand that part very clearly. So in this All Things Tensor tutorial, we talk a lot about tensor, and this Jupyter notebook is also going to be available in this DeepWorks GitHub repo at this PyTorch tutorials location. So let me move it. So this Jupyter notebook is going to be available at All Things Tensors. Now this All Things Tensors Jupyter notebook is available here. At the end of this All Things Tensor tutorial, I would suggest you to please experiment this Jupyter notebook with variety of tensor operations, definitions, so you could learn the basics and the fundamentals of the tensors. That's all I have for you in this tutorial. I'm going to see you in my next tutorial. Until then, thank you so much.